Hello guys, welcome to my YouTube channel. And my name is Rimaldo Ansle. And I'm going to take you through uh, a paper review of modeling the dynamic relationship between spread of infection and observed crowd movement patterns at large scale events. And our group project title is related to that project. And our group project deals with crowd prediction using deep learning models. So I'm going to take you through the introduction. Yeah, the introduction. The the paper generally focuses on crowd movement at large events and their impact on infection spread. So they are literally trying to solve a problem of disease spread on crowded places, for example, concerts. And in this case, they had to choose two cases of concerts whereby one is a football match concert and another one is a music festival. So the data source, they utilize the Wi-Fi mobility data from events at two different stadiums, and they used people's phones and smart devices, for example, smartwatches, to detect movement among the crowds. So the key findings there were contact duration distributions, and they explore different random walk models for infection spread. Yeah. The conclusion, the need to refine models assessing infection risk at mass gatherings was the conclusion of after this project. Yeah. So the computational problem, like I'd already discussed, is the quantitative framework for assessing infection risk and its impact on disease transmission. And it involves several models and patterns. So one of the patterns, the model contact pattern, this is how contact patterns emerge from crowd movement, how people end up contacting each other when they are in a crowded place. And the infection spread models, this is how the diseases are spread, for example, through contact, through breath, and other factors. Yeah, how they used 5 models, and one of the models is the random walk models, which are used to simulate model, and and this is a comparison model that assumes pedestrian contacts are analogous to collisions in a gas. Then the third one is the correlated random walk, which is a model that includes directional persistence in movement patterns. Then the fourth one is the continuous time random walk, which is a variation of random walk model that incorporates between intermittent movement behavior and persistent movement behavior. Then the fifth one is the Edo-Srini model, which is used among a pair of nodes. And for this case, in their project, they used a probability over that. Yeah. So the next slide analysis. And this is the first model I use. So in this model, the people move in an intermittent way, and this is explained by a factor that people at some point will be moving, and at some other point they will be seated. In this case, they are focusing on the football stadium, and it's found in both the football match and the dance event, but it's more in the football match event because naturally a person may stay in one place, and when it comes to the dance event, movement is based on the dance. They are not dancing, they're just standing, for example, like bodyguards or something. So this leads to a pattern of people stopping at different variations, locations, and different times. Yeah. So this is one of the graphs that shows the intermittent and the persistent movements. And the first two show the 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 football match capture of the people. As you can see that the dots represent the signals that were captured. Then this is image A and image B. They represent the football match graph. Then image C and D, they represent the dance concert graph. Then this can be explained by the waiting times. For example, by dividing space between the individuals, counting the number of consecutive intervals a person stays in the same place, and this is different statistical models basing on the waiting time distribution. Yeah. On the next one, we have the distribution of the waiting times on log scales. So we have different, as I said, they use different statistical models. As you can see, there is an exponential, truncated power law, stretched exponential, and the log normal method. So now in the case of this project, the truncated power law was better suited for this specific project because it takes a limited event duration. Events have a limited time duration. They finally end. It's not a persistent thing. Then the next thing we have the aggregated contact networks. So this is a is the way people are interconnected, the way people can meet and contact each other in a crowded place. So it compares with the theoretical distribution, which is a Poisson distribution that assumes random connections. People who are in a crowded place randomly connect to each other through contact, through breath, and all that. So the actual degree distribution is not heavy-tailed, meaning that the graph wouldn't show a surprising number of people with an extremely large number of contacts. In brackets, the super spreaders. There might be some variation, but most people would likely have a similar number of contacts. Some people may have, most people, are most probably going to have the same number of contacts at the end of the day. This means that the super spreaders might be less common than the people who are overspreading the disease, might be less common than expected based on the movement patterns alone. So there are two types of aggregated contact networks, but before I explain those, I'd like to show you how an aggregated contact network looks like. So these blue, the dark blue are the dense are the contacts that sparsely spread that spread the most. Then the less are the less contacted people. Then the blue ones are the highly contacted people, meaning that these people are most likely able to spread the disease among the crowd. Then going back, they have two scenarios of aggregated contact networks, and one of them is a dense, where there are many connections between people in the network, which is evident in this picture, which is the one where people can't connect to each other more often. Then in the next slide, we have the empirical degree distributions together with the voice distribution. And these have different outputs. As you can see, it's, this is the one that has the concert, and this is the one that has the football match. For the for the one that has the football match, it's kind of normally distributed, while the one that due to the one that has the football match is kind of normally distributed settled in one place. While while for the concert, most people are going to be moving around, which is a different output. It's also explained by other models. In the next slide, the exponential and the power law splits, whereby, like I had explained earlier, you can see how they are distributed, whereby the blue ones are for the football match, then the red ones are for the for the for the concert, for the dancing concert. So in this case, you can see that using the truncated power law, most of the people are analyzed compared to the exponential method. Then the random walk models. So these people were able to use random walk models to mimic these movement patterns and see how infections spread in simulations. The two main characteristics they focus on are persistence, how long the person keeps moving in the same direction, and intermittence, which is explained by how people alternate between moving and resting. To mimic intermittent movement, they divide each random walk into periods of movement and rest. For example, for the football match, they stimulate breaks where everyone stops moving for a while. For a dance event, they use a stochastic approach where each person randomly decides how long rest before moving again. So how long they are going to rest. Like for a football thingy, they can be able to tell that right now people are going to rest, and they can use a different approach. And of course, they use a different approach for the dancing event. People, so next slide, I have the resulting weight distributions, the random walk, the different methods that they used, as you can see in this image. Then in so I was explaining the different work models. So the first one is the random walk, and the second one is the regularized continuous time random walk, and the third one is the continuous time random walk. And this is how they were applied in the project to give different outputs, as you can see in these graphs, A, B, and C. Then the transmission over the network. In this section of the study, they look at how two types of intermittent crowd movements where they have regulated and stochastic affect the spread of infection using simulations where the population density stays constant. Real life events